Hello mathematicians. We now take a look at exponential functions as a follow-on to our log function work. Now the exponential function itself that we look at is probably best understood by having a little look at the curve to start with. So we might have a look at the GeoGebra curve and pick out what we can there before we start looking at text. So you would remember the exponential curve y equals a to the x. Runs off towards 0 as x tends to negative infinity, always cuts through the y-axis at y equals 1. So when x equals 0, y equals 1, and runs off to infinity after that. And as we change the value of a, the value of a that we're particularly interested in at the moment is e, which is an irrational number. We'll come back to it more. But the thing about all of our exponential curves is that as well as passing through the y-axis at a value of y equals 1, there's a certain relationship between their slope and the value of the y-coordinate. And this is outlined most strongly when we look at the y equals e to the x curve. And if you simply look at this one point, as with any point on this curve, you can see what the relationship is. And that is that the slope of the tangent on the curve of y equals e to the x is the same as the y value. So the slope of the tangent is always the same as the height of the curve. So you can see that as I change the y value here, which of course changes the x value, but as I change the y value, it's going to always equal the slope of the curve. And that gives a really interesting result at 1. I can't quite get it onto 1. But you can see that at x equals 0, y would equal 1, and the slope of the tangent would also be 1. Or in other words, it makes an angle of 45 degrees with the x-axis. So let's go with that picture in our mind, that the height of the curve and the slope of the curve are the same, and look at how that can be expressed both in text and mathematically. So to my mind, the biggest challenge in this first exercise is not actually doing it, it's getting your head around what it's telling you. And we know how important that idea of understanding is. So what we're going to say is that there exists a value of the base, a, in y equals a to the x, for which the slope of the curve at the point where x equals a is the same as the y value. So we've seen that on the graph so far. That value is e, an irrational number which is given approximately, that's an important bit, by 2.718, but because it's irrational it goes on forever without a recurring pattern. Now that's the text statement, but in terms of writing that mathematically, that's just this. Because it says that the differential of the curve, e to the x, is the same as the y value of the curve, e to the x. So for the curve, y equals e to the x, sorry about my writing there, for that curve, y equals e to the x, then the differential of e to the x is the same as e to the x, which is a very important property. Now, just as with the log function, we talked about log base e as the log function, then e to the x is called the exponential function because there are a whole family of exponentials, a to the x. Now this little part will take some real getting your head around, I think. So this is a proof. So we saw a geometrical description of this with GeoGebra. This is a mathematical proof. If y equals e to the x, then we can say that x equals log base e of y. Now we can either say that because of our definition of logs, or we could take log base e of both sides, so log base e of y, so that's this, equals log base e of e to the x, and we know they're opposite operations, so they cancel each other out. So whichever way we think of it, we get this relationship. Now, if I say then, well, I've got an equation with x as the subject, y is the variable, then I could say, therefore, dx dy, because I'm going to differentiate x with respect to y, And we know that the differential of a log is the differential of what we're taking the log of. So differentiating y with respect to y gives us 1, and that's put over what we're taking the log of. So dx dy is 1 on y. But we want dy dx. Dy dx is 1 on dx dy, which is 1 on y, which is y, which is e to the x. So this is a formal mathematical proof of this relationship just here. Take your time, get that under control, it's worth it. Now, if we have something more complicated than just e to the x, so e to the f of x, then by the chain rule, the derivative of e to the f of x is f dashed of x e to the f of x. Now this is what we'll use 99% of the time without thinking more about it. But again, it's worth knowing where this comes from in case you encounter that 1% problem. So this is the formal application of the chain rule to that problem. So if y equals e to the u, where u in turn is some function of x, so in other words, y equals e to the f of x, then by the chain rule, dy dx equals dy du dx. So that means that dy dx equals dy du, so the differential of e to the u is e to the u by du dx, and du dx also can be written as f dashed of x if we change the variable back. So dy dx is f dashed of x e to the f of x. Again, take your time, trace through it. It's not something to commit to memory, but it's good to understand. Now, if y equals a to the x, so we're talking about, in this case, differentiating an exponential where the base is not e, then it's more complex. We probably only need to remember the final result, but we need to, again, think about it in case we're stuck. So if y equals a to the x, we're going to make use of this fact here, that e to the log a is the same as a, because the exponential of the log cancel each other out. So if that's the case, we can write y equals a to the x as e to the log a raised to the x. Then we can use our power rule for indices to multiply these two powers together. So we can say y equals a to the x is the same thing as e to the x times log of a. And then dy dx is going to be, if we just use our rule up above, we differentiate this power up here. So log a is just a constant, remember. So the differential of x log a is log a, and we multiply that by e to the x log a. So that's then log a times, and e to the x log a we saw was the same thing as a to the x. So it's log a times a to the x. So if, for example, we were differentiating, say, 2 to the x, if we had y equals 2 to the x, then dy dx is going to be simply log 2 times 2 to the x. Okay, now again, 99.9% of the time we will just use that relationship because of memory. But if we forget it, we know where it comes from. Now, those who might want to dabble in implicit differentiation, I won't talk us through this because it's not Extension 1, but Extension 2 students could follow that through. Extension 1 is free to use implicit differentiation. If you like it, you can do it. Personally, I think it is more elegant, but it's not part of your course. So, let's look at using the chain rule to differentiate. Now, there are always marks all over the HSC paper to be gained by just applying this rule. So if we've got y equals e to the 1 minus x squared, so we've got e to the f of x, then we know that dy dx is f dashed of x times e to the f of x. So dy dx is the differential of 1 minus x squared, which is minus 2x, multiplied by what we had, e to the 1 minus x squared. Now there's nothing much we can do to simplify that now, so that's it. If it comes to something more complicated, or more complicated, like in part B, then we might do a little bit of algebraic simplification. So in this one we've got y as e to the f of x, and that in turn is part of a function. So we've got a function of a function, or a chain rule if you like, and when we apply that, we do the function of a function, so 4 times what's in the brackets to the power of 3, multiplied by the differential of what's in the brackets, and then tidy it up with algebra. For the next one down below, we can see that we've got a product, or at least until we do see that we've got a product, so that multiplied by that, there's really not much we can do. Once we see that we've got a product, we know the product rule. So by the product rule, put down the first, differentiate the second, plus put down the second, differentiate the first. And now, as often gives us trouble with product rule, take out common factors and tidy it up if we can. So we can see that we've got an x squared which is common and an e to the x which is common, so that gives us this when we've tidied it. And in the next one, again a product, we've got that multiplied by that. So product rule again, take out your common factor. You might wonder why you'd bother taking out your common factor. Well, the reason is that later on we'll see that we use dy dx as a guide to getting turning points, and we know that turning points occur when dy dx equals 0, and if we've broken things into a product like this, then if this is 0, which is impossible because e to the x doesn't pass through 0, or this is 0, which will happen at x equals minus 1/5, then that locates our turning point for us. Okay, find the derivatives of these. So we can see hopefully that what we've got here is a quotient. So we apply our quotient rule. So take the denominator and square it, then put it up the top, multiply it by the differential of the numerator, minus, put down the top, multiply by the differential at the bottom, and again, work on it algebraically to see if we can make it look simpler. Not a lot, but that's, again, perhaps useful for getting a turning point. For the next one, again, we've got a quotient, so we apply exactly the same rule really carefully, and there's not much we can do to make that look nicer. Number 5, or the example here, called number 5, find the gradient of this curve at that point and show the gradient is 5 times the height. Well, we should be expecting that because we know that there's some link between the gradient and the height. So, even though it's not essential, draw a picture, just to get your brain thinking in the right way. So when we do that, we've got our curve of e to the 5x. We know that it passes through 1. So this point here is 1. And we're interested in the point a, e to the 5a, and we want the gradient at that point. So as always, to get the gradient at the point, we need to find the slope. So that means that we need to differentiate. So when we differentiate the curve, we get that. And we can see that that means that the slope of the curve at the point where x equals a is 5 times e to the 5a. And of course, e to the 5a is the height of the curve. It's the y value. So this is that statement in words written more formally, that the slope of the curve at x equals a is equal to 5 times the y value of the curve at x equals a. So these are the numbers that I'd like you to have a go at. This really needs to be bedded in well for us to just use it automatically later on. But before you do have a go at that, think about what the big idea has been in this little section. What are the 2-3 facts that you can carry away from this that you hope to be practicing over and over and over in the exercise?